Good day, everyone. You're welcome to study section C of our course, Linear Algebra 2. So today we are looking at bilinear and quadratic form. If you can still recall of all our previous discussions on equations, you see that we have dealt with the linear equations, how to solve them. But today we are going to discuss another form of equations, which is the quadratic, the linear and quadratic form. And when we are talking about linear equations, you can see it in the form of equation 1, of which we have treated before, where you have your a1 x1 plus a2 x2 and so on to an xn equals b, where your ax a1 x1 a2 x2 and so on to an x2, which is your equation 2, are functions of n variables x1 x2 up to n. This left hand side of equation 1 is called linear form. There's no doubt about that. We have solved series of examples of this linear equations, where all variables occur to the first power and there are no products of variable in the expression. You can see the powers of the variable is just 1. It's not risen to the power is not greater than 1, and there is no product of variable in the expression. So you don't have x1, x2, there's no products. So we want to look at functions in which the terms are square of variables or products of two variables. These types of functions arise in varieties of applications, such as geometric, variations of mechanical systems, statistics, and electrical engineering. These are the areas, these are the applications area where you can see this form of the equation. So definition now. A quadratic form in two variables, say x and y, is an expression that can be written as ax squared plus 2bxy plus cy squared, such that your ax squared plus 2bxy plus cy squared can be written in a matrix form. This is an equation giving us a quadratic form. You can see here the difference between these particular equations and the previous one that we have dealt with, like in your equation 1, is that you have a product of the variable where you have your x, y is a product. Then you can see the power of x is no longer 1 here, it's raised to the power of 2. That makes it to be a quadratic form. So, and these particular equations can be transformed, can be written in a matrix form, which is equivalent to a vector, which is x, y, then a 2 by 2 matrix, which is a, b, b, c. Then you have a vector, a column vector, x, y. If you perform the operations on this one, that is to multiply the matrix, you will discover that you will have the equation back. So you multiply the vector, the row vector, x, y, multiply it by 2 by 2 matrix and see the product. Then whatever your answer is, multiply it with the column vector x, y. Then you discover that you have the equation back. So you can be given a quadratic equation and you have to transform them into a matrix form. Quadratic form. Let's look at the example that we have here. Example 1. 2x squared plus 6xy plus 7y squared. You can see here, from what you have, the standard form of a quadratic form is ax squared plus 2bxy plus 6y squared. So look at that equations and compare it with the equations you have in the example 1, which is 2x squared plus 6xy plus 7y squared. You can see that the coefficient of x squared, which is your a from the standard form, you compare it, you can see that your a is equivalent to 2, where the coefficient of xy, the coefficient of xy from the standard form is 2b. And from the example given to us here, the coefficient is 6. So from there, you can easily get your b, which is 6 divided by 2, and it gives you 3. That's how we got our b to be 3. Then c, that is c is standing for the coefficient of y squared. And the coefficient of y squared from the example here is 7. So we are able to get the coefficient now, which is a equals 2, b equals 3, then c equals 7. So from there, the equation given to us, which is the quadratic equation given to us, which is 2x squared plus 6xy plus 7y squared, is equivalent to a row vector. That is, we have a xy, then we have a 2 by 2 matrix. The 2 by 2 matrix are the coefficients of x, dx, and coefficient of x squared, the coefficient of xy, and the coefficient of y squared, which is given as ab, then b, c. So it's given here as 2, 3, then 3, 7. Then multiply by x, y. I hope that one is clear enough. Then let's look at another example where you have the quadratic equation as x squared minus 3xy minus 2y squared. From what you have here, compare the equations you have here with the standard form, with the quadratic standard form, which is x squared, ax squared plus 2bxy plus cy squared. So you can see that the coefficient of x squared from the example 2 is 1, and the coefficient of xy, which is 2b, is to give us minus 3. That is, 2b equals minus 3. So easily you can get your b, which is minus 3 over 2. Then the coefficient of y squared, which is minus 2, and that is our c. So easily you can form your matrix here. Your matrix 2 by 2 matrix, which is 1 minus 3 over 2, then minus 3 over 2, then minus 2. So you can easily show this. If you are given a matrix, a matrix in form of this, you can multiply them and get a quadratic equation. B, a quadratic form of n variables. Since we are talking about the generalized form now. The quadratic form of n variables, x1, x2, up to xn, is an expression that can be written as x1, that is the vector x1, x2, up to xn, then multiply by a, and you know your a is going to be n by n matrix. multiplied by the column vector, which is x1, x2 up to xn. So we are talking about the generalized form now. Note the previous example now is just 2 by 2. It's 2 by 2 matrix. Your A is 2 by 2 matrix because you are dealing with a quadratic, which is 2. That is the highest powers of the variable, it will be 2. So you are going to have 2 by 2 matrix. So if you are having an n variables now, that means you are going to have a matrix of n by n, matrix A to be n by n matrix. So where your A is a symmetric matrix of order n, it will be a symmetric matrix of order n. If x is transpose, that is, you can transpose your x. Therefore, a quadratic form of the form of that equation you can have. That is, if you transpose your the vector, you have your x transpose multiplied by a multiplied by x. So the matrix, the nature of that matrix must be a symmetric one. If you look at your example 1 critically, you will see that we have AB, then BC. This is a transpose. This is a symmetric matrix. It's a symmetric matrix. I believe you can still recall what a symmetric matrix is. Let's look at another example here. If x is equal to x1, x2, x3, that is a column vector, then your A is given as a 3 by 3 matrix, which is 1, 2, minus 1, 2, 7, 3, minus 1, 3, minus 3. You have to show that S transpose A X is a quadratic form. That is, when you multiply this parameter together, you will have a quadratic form. That is, the equation will be a quadratic. So let's look at that. Let's look at how to go about that. So we have given our x. So you transpose that x. If you transpose it, you will have x1, x2, x3. Multiply by your A, which is 3 by 3 matrix, then multiply by the column vector x, which is x1, x2, and x3. If you can still remember from your multiplication when you are multiplying a matrix. So you are going to multiply the row with the column. So row 1 will multiply column 1. You know, you're having just a row for your x transpose. So that row, you use it to multiply column 1, column 2, column 3. And that is what you have here, which is x1 multiplied by 1, you have x1. x2 multiplied by 2, you have plus 2x2, then minus x3, that is x3 multiplied by minus 1. That is for column 1. Then use that x to multiply your column 2. You will have x1 multiplied by 2, which is 2x1, plus 7x2, plus 3x3. So you are using that row, your x, to multiply the column on a matrix A. So you have it as column 2. Then use that row, that your x, to multiply what you have in column 3. So you have minus 1, minus x1 plus 3x2 minus 3x3. That is column 3. So successfully we are able to multiply the transpose of x with A. So we are left with the last one, which is the column vector x1, x2, x3. So we want to multiply this now. You are multiplying the row with the column. So you are going to take what you have here on the column 1, which is x1, 2x2 minus x3 to multiply x1. So that is what you have here. Then 2x1 plus 7x2 plus 3x3 to multiply your x2 plus minus x1 plus 3x2 minus 3x3 to multiply your x3. And that is what you have here. So by the time you open up the bracket and you simplify the expression, you will have what you have here, which is x1 squared plus 7x2 squared minus 3x3 squared plus 4x1 x2 minus 2x1 x3 plus 6x2 x3. So that means we have gotten our quadratic equations. You can see the powers of those variables. The highest power is 2. That makes it to be a quadratic. Then you have the coefficients of those variables, x1, x2, x3. Then you have the products, where you have your x1, x2, x1, x3, then x2, x3. So in a general form now, you can represent it as a11 x1 squared plus a22 x2 squared plus dot 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 to an xn squared. That is, those that have the powers of 2, the first one, plus the summation. The summation is when your high is not equal to your j. That is, your high can be 1 and your j be 2. So they are not equal. It's when they are equal that you have a square of the variable. When you have x1 square, x2 square, x3 square, and so on. That is, that your high, the row, is equal to the column. But if they are not equal, they are going to have the product of those variables, which is xi, then multiplied by xj. You correct that. xi multiplied by xj. That is the quadratic form. So the summation from I not equal to j or ai x1 and xi xj is not 1, it's ij. So you are finding the product of the two, because they are not the same. I is not equal to j. Note, the coefficient of the square term, x1 square, x2 square, x3 square appear on the main diagonals of the matrix 3 by 3 main diagonals of 3 by 3 matrix. You can see that is when your high is equals to j that you have the coefficient of the x1 square, x2 square, x3 square. So they appear on the main diagonal of the matrix. So if we have 4 by 4 matrix, we are going to have the same thing. It should be at the diagonal. 2. The coefficient of the cross products. The coefficient of the cross products, that is, when your height is not equal to j, the terms are each split in half. They split in half, appear in the off-diagonal position as following coefficients of positions in the matrix A. That is, when you have the coefficient of x1, x2, so you will have the value as a1, 2, and a2, 1. Then the coefficient of x1, x3, it will give you the product of a13 and a31. So the coefficient of x2, x3, it will give you the product of a23 and a32. So you can note that Si, Sj is the same thing as Fj, Xi, because we are talking about symmetry A. So the product, you can say 2 times 3 is also the same thing as 3 times 2, because the product of the two will give us 6. So those are the key things you need to know. The diagonal, the coefficient of the square terms will be at the main diagonal, while the cross product terms are split in half and appear in the off-diagonal position. And you know the product, which is xij is equal to xj xr. So next one, we are looking at the maximum and minimum values of a quadratic form subject to a constraint. You want to find the minimum and the maximum value of a quadratic form that is subjected to a constraint value. Let's look at this theorem before we solve example. Suppose A is a symmetric matrix of order n, and its eigenvalues in ascending size order are lambda 1 less than or equals to lambda 2, less than or equals to lambda, and so on up to lambda n. If x is constrained, if a condition is given to n that the modulus of n, that is, you are finding the unit vectors of n now, is equals to 1, that is the constraint, that is the condition. The condition is that by the time you find the square roots of the squares of those variables, it gives you unity. This is equals to 1. That is the constraint. Then, lambda 1 less than or equals to the transpose of x multiplied by ax is less than or equals to lambda n. Take note of this. Then, the transpose of ax multiplied by ax is equals to lambda n. If x is an eigenvector of A corresponding to lambda n, that is, for each value of your lambda, you will have an eigenvector of A. And the transpose of x multiplied by ax is equal to lambda 1 if x is an eigenvector of A corresponding to lambda 1. That is, on each values of your lambda, you will have eigenvector. On each values of your lambda, you will have eigenvector. You have the corresponding eigenvectors of A. So, therefore, from the theorem above, it follows that Subject to the constraint of the modulus, that is the the normalized of the x is equal to 1. The quadratic form of x transpose multiplied by ax has the maximum values of lambda n, the largest even value. This is the largest even value. The values of your lambda, if it is the highest, so you have the maximum value. And a minimum values of lambda 1, meaning the lowest eigen value. That is, the transpose of x multiplied by ax is maximum for lambda n and minimum if otherwise. That is, those values of your lambda will determine the maximum and the minimum value. So let's look at the example that we have here. Find the maximum and the minimum values of the quadratic form this. Find the minimum and the maximum value of the quadratic form x1 squared plus x2 squared plus 4x1 x2 subject to the constraint x1 squared plus x2 squared equals 1. This is the constraint condition. And this is the quadratic form. You have quadratic equations given to us. So you start from your quadratic equation. So the quadratic form can be written as that if you are going to transform this equation into a matrix form where you have your x transpose, you have your A, then you have your column vector x. So from here now, you can see that your x now is going to be x1, x2. That is, you are having 2. So the matrix you are going to have here is going to be a 2 by 2 matrix. And your x, the transpose of x is x1, x2. Then multiply by your A. How do you get your A from here? You know A, which is the coefficient of x squared. You know your B. You know your C. You have AB, then B, C from the matrix. So the coefficient of x now, x1 is 1. Then, which is your A. Then your B. Your B here is from the standard form is 2b xy or x1, x2. And you can see that the coefficient of x1, x2 is giving us 4. So that means your 2b is equal to 4. So you will get your b from that by dividing what you have here by 2. So you have 4 divided by 2, which is 2. So you have your b as 2. Then the coefficient of your x2 now, x2 squared is 1. You can see the coefficient. The number in front of the variable is what we call the coefficient. So that is 1. That is 1. So you multiply them now. The standard for you to get your lambda, you can still recall from our characteristic polynomial. When you find your delta, you find the determinant of a minus lambda I. You find the determinant equals to 0. So the quadratic equation equates it to 0. So the same procedure is being applied here. So your A is a 2 by 2 matrix, which is 1, 2, then 2, 1. You can see this matrix is a symmetric matrix. It is symmetric. Those are the conditions. It's a symmetric matrix. Then multiply by lambda. Lambda is what what you want to get. You want to get the values for lambda. Then multiply by your height. And that height is what? Is the identity matrix. So the identity matrix for 2 by 2 matrix is 1, 0, 0, 1. So by the time you open up the bracket, you multiply, you will have 1 minus lambda, then 2. Second row, you have 2, then 1 minus lambda. The coefficient of x2 squared is 1, not minus 1. It's 1. So that is why we are having 1 minus lambda, then 1 minus lambda on the other side. So from what you have there now, equality is 0 and find the determinant and equality is 0. So you are finding determinant. You are using 1 minus lambda to multiply 1 minus lambda minus 2 multiplied by 2. That is the determinant, which is equivalent to 0. And it's given here, the first line. So you have 1 minus lambda multiplied by 1 minus lambda minus 4. So by the time you open up the bracket, you will have lambda squared minus 2 lambda minus 3, which is equal to 0. This is a quadratic equation. So you solve that, you will find the values for your lambda, and it's going to give you 2 values because the powers of lambda is raising to the power of 2. That means you are having 2 values for your lambda. So when you solve that, we have lambda equals 3, then lambda equals minus 1. Therefore, the transpose of x multiplied by ax is maximum. You can see the value. You have 3 and minus 1. The biggest one is 3, so it's maximum at that point. So it's maximum when lambda is 3 and minimum when lambda is minus 1. And it's subject to the constraint x1 squared plus x2 squared, which is equals to 1. So the next thing now is to find the corresponding eigenvalue for those lambda. We want to find the corresponding eigenvalues for those lambda. To find the values of x1, x2 at the maximum and minimum points of the lambda, we have to find the eigenvector corresponding to this value and normalize this eigenvector to satisfy the condition. We normalize this eigenvalue to satisfy the condition, and the condition is x1 squared plus x2 squared equals 1. We find the corresponding eigenvectors for lambda equals 3. If you go back to the standard form, from your previous knowledge, you have been taught in your 203 how to find the eigenvalues and eigenvectors. We also did it in the previous studies. So from here, you have gotten your lambda. So go back to that equation where you have your 1 minus lambda, then 2 is equal to that matrix multiplied by your x1, x2, which is the column vector is equal to 0. So the next thing is just for you to substitute the values of lambda. So when you substitute the values of lambda into that matrix that you have here, you see that 1 minus 3 to give you minus 2, then 2, 2, then minus 2. So you're able to get the matrix. Then the next thing is to multiply. You are multiplying the matrix A by the column vector x1, x2. So when you multiply that and equals to 0, you have your equation 1 and equation 2. So minus 2 multiplied by x1 plus 2 multiplied by x2 equals 0. Then the second row, you are having row 1, row 2. So 2 multiplied by x1 minus 2 multiplied by x2 is equal to 0. That is where you have your equation 1 and equation 2. So this is a simultaneous equation. If you solve them, you will have your eigenvectors to be 1 and 1. So you have x1 to be 1, then x2 to be 1. So the next one, we are finding the corresponding eigenvector now when lambda is 3. So we want to find the corresponding eigenvector for lambda equals minus 1. So you are going to substitute. Anywhere you are having lambda, you replace it minus 1. Then you have your equation 3 and your equation 4. When you solve these equations, you will have the values for 1 and x2, which is a 1 and 1. So the basis for the eigenspace lambda equals 3 is given as 1, 1. Then for lambda equals minus 1, you have 1 minus 1. So for us to normalize this now, how do you normalize this? You have gotten your x, you find the modulus, that is the square, the summation of the square. You find the square root of the summations of the square. You have 1 square, the root of 1 square plus 1 square. So you find them. Then you get that. Then you find the formula for normalizing a vector. So the formula is given as xi equals to xi over the summation of the square root and the square of x. That is, you can have, if you are having a x1, x2, x3, so you are going to find the square of those ones. Then you find the square root of everything. So the normal one now, the normalizing form now is xi. That is your x1, which is 1. Then when you find the root, you find the square, the root of the square of all the vectors you have here. You have it as a 2. That is root 2. So for point 1 now, for the first one, for your x1, you have 1 over root 2. Then for your x2, you have 1 over root 2. That is for lambda equals 3. For lambda equals minus 1, you also find the normalized form of it, which is xi, and your xi is 1. Then you find the root of the squares, 1 square, then minus 1 square. You add them together, then you find the square root. So you are going to have root 2 also. That is why you are having 1 over root 2, then minus 1. When s2 is a minus 1, you have minus 1 over root 2. So therefore, subject to the constraint x1 square plus x2 square equals 1, the maximum values for x1 and x2 are 1 over root 2 and 1 over root 2. So subject to that constraint now, and the constraint is that when you find the modulus, of those variables, the modulus means you find the square of all the variables that you have, find the square of it and find the square root of everything. Then this to divide those things. So that is the constraint, and everything will be equal to 1. So that is the condition, and the condition has been met here. So at the maximum values of x1, x2, when your lambda is 3, is given as 1 over root 2, then 1 over root 2 respectively. Then the minimum value, you have the minimum value as lambda equals minus 1. So you also have the corresponding normalized one for those values, which is 1 over root 2 and minus 1 over root 2 respectively. So suppose now your lambda is minus 1. Suppose your lambda is minus 1. The alternative basis for the eigenvalue can be obtained by multiplying the basis vector by the basis vectors are both by minus 1. That is, it's just to multiply by negative 1. So just reverse the sign. When you reverse the sign, what will happen to those values? Thus, the maximum values of lambda occur if x1 is equal to minus 1 over root 2, then x2 equals minus 1 over root 2. Already you have it as 1 over root 2, then 1 over root 2. So the difference is that negative will affect the value, and vice versa for lambda equals to minus 1. Originally you have 1 and minus 1. So you have it as 1 over root 2, then minus 1 over root 2. So when the sign change, the one that has positive before, we have negative. The one that have negative before, we have positive. That was all. About that. So we have another example here. Example slash exercise. So there are some missing steps there. So on your own, you can sit down and sort them out. How you arrive at that. Find the maximums and the minimums values of quadratic form, subject to the constraint x1 square, x2 square, x3 square equals to 1, and determine the values of x1, x2, x3 at which the maximums and the minimums occur. The point at which the maximums and the minimum values occur, you determine the values of x. You determine the values of your x, x1, x2, and x3. And the questions are given here. For Roman figure 1, you have x1 square plus x2 square plus x3 square minus 2x1, x2 plus 4x1, x3 plus 4x2, x3. You have the second one, you have the third one. So we only consider the first one here. So the remaining Roman figure 2 and 3, go and do them and upload as assignment. So solution to the solution to the Roman figure 1 now. Given x1 square plus x2 square. So from here now, you can have the coefficients of those values, and the coefficients are what? A11, A22, A33, A12, A13, A23. So you use those ones to form your matrix. You form your matrix A from the equations that have been given to you. From the explanation, you know the diagonal. The main diagonal will be what? Will be when I is equal to j, that is where you have your square. So your x1 square, x2 square, x3 square. The coefficients will be at the diagonal. And what are the coefficients of those variables? You have 1, 1, 1. The coefficient of x1 is 1. The coefficient of x2 square is 1. The coefficient of x3 square is also 1. So the one at the diagonal. Then your bx, your 2bxy, you know how to sort that one out. by getting the values, the coefficients of those ones. So you have your A11, A12, A13 are 1, 1, 1 respectively. Then you have the coefficients now. A12 plus A21, which is what? Is minus 2. That is when you have the product of x1, x2. When your I is not equal to j. I is 1 here, j is 2. So by the time you multiply the two together, you have the additions of the coefficients of those variables, which is x1, x2. So the addition is what you have here as minus 2. So if the addition is giving you minus 2, you know how to get your A1, A12, and A21. So it will be that you have added two things together that gave you minus 2. So if you want to separate the things now, the two things now, that means you're going to divide by 2. So you have your A1, A12 to be minus 1, then A21 to be minus 1. That was what we did here to get our matrix A. So you have 1 minus 1, 2, minus 1, 1, 2, then 2, 2, minus 2, 2, 1. So you can see that a matrix A is a symmetric. It's a symmetric in the sense that you can transpose A, you will still have your A back. Recall from the previous knowledge, a symmetric matrix. When you find the transpose, it's also giving you the same matrix. So those are the conditions for you to solve this particular problem. It must be a symmetric matrix. So the next one is to determine the maximum and the minimum values of A, or eigenvalues of A, and the eigenvalues are your lambdas. So you take your characteristic equation where you have the determinant of A minus lambda I. What is your I? Is a identity matrix. An identity matrix. So you use that identity matrix to multiply by your lambda. Then you find A minus lambda I now. So when you do that, you will have the matrix here. And the next one is to find the determinant. Now to find the determinant, you are picking 1 minus lambda, then you cancel the row completely, the row 1 and the column 1. So the remaining entries that you have there, you multiply them and you subtract. So you are going to have 1 minus lambda multiplied by 1 minus lambda minus 4 for that one. Then you also do for the column 2. You do that. When you follow that normal steps, you will have your equation as lambda raised to the power of 3 minus 3 lambda squared minus 6 lambda plus 16 equals 0. So this is a polynomial equation whereby you get the values for your lambda. So the powers of lambda is raised to the power of 3. So you are going to have 3 values for your lambda. You have 3 values for your lambda. When you solve that, your lambda 1 will give you 2. Your lambda 2 will give you 1 plus root 33 over 2. Then lambda 3 will give you 1 minus root 33, everything over 2. So having gotten the value, the eigenvalues now, we want to find the corresponding eigenvectors for those values. And from the values we have obtained here, you can determine the minimum and the maximum. The maximum one will be your 2, which is the highest value for lambda. Then the minimum one will be the lowest value, which is lambda equals 1 minus root 3 over 2. So the next one is to find the values, the eigenvectors now. Go back to that the determinant. Anywhere you see lambda, replace by 2 for lambda 1. So when you do that, you will have what you have here, which is minus 1, row 1, minus 1, minus 1, 2, then row 2, minus 1, minus 1, 2, row 3, 2, 2, minus 1, multiplied by a vector x, that is the column vector x, x1, x2, x3. So by the time you multiply this one together, you will have 3 equations. So you solve the 3 equations simultaneously from what we have treated before, solve it simultaneously and get the values for your x1, x2, and x3. So it will give you your x1 will give you 1, your x2 will give you minus 2, minus 1, then your x3 will give you 0. So the same thing is applicable for your lambda 2. For your lambda 2, you follow the same procedure. You put in the values of your lambda into that determinant, then you multiply by the column vector x. So you get 3 equations also. You solve them simultaneously and get the values for your x1, x2, and x3, which will give you minus 1, 1, and 0. So normalizing this now, I've explained how to normalize by finding the summation, the square root of the summation. You square those values, then you find the square root of it. So then you use it to divide those values. So you have 1. When you do that, 1 square plus minus 1 square plus 0 square, everything will give you 1 plus 1 plus 0. So find the root of that, find the square root of that, you will have root 2. So to normalize it now, it will have 1 over root 2, then minus 1 over root 2, then 0 over root 2, which is 0. So you have that for the maximum value, which is lambda equals 2. So for lambda, for the minimum value now, for lambda equals 1 minus root 3 root 33 over 2. So you also repeat the same procedure. You substitute the values of your lambda into that matrix and you multiply by the column vector x1, x2. So you have 3 equations. Then you solve simultaneously to get the coefficients of the values for your x1, x2, and x3. So for that, the values are given here. The hidden space are given as 1 plus root 33 over 8, then 1 plus root 33 over 8, then minus 1. Those are the hidden vectors for lambda for the minimum values. The minimum values. So the next one we want to look at the positive definite matrix and a quadratic form. Positive definite matrix and quadratic form. Definition now. A quadratic form A transpose multiplied by AS is called positive definite. We can say a quadratic form is a positive definite if, these are the conditions, if the transpose of A of S multiplied by AS is greater than 0. It's positive if you have it as greater than 0. For all x not equals to 0, that is your vector x, they are not equals to 0. Well, when you do the matrix multiplication, the transpose of s multiplied by a multiplied by s is greater than 0. That is the first condition. A symmetric matrix A is called a positive definite matrix if the quadratic form, the x transpose S multiplied by AS, is positive definite. That is, if that symmetric matrix is also a positive definite matrix, that is, the product of transpose of A and transpose of S multiplied by transpose, the product of S transpose A and S is greater than 0. If you have a positive value for it, that means the matrix is positive definite. The quadratic matrix, the quadratic form of that matrix is a positive definite. Let's look at theorem 6 towards that. A symmetric matrix A is positive definite if and only if all the eigenvalues of A are positive. The condition is if and only if all the eigenvalues of A, that is, all your lambda, are positive, then that symmetric matrix is positive definite. It's a positive definite. If the values of your lambda are all positive, but if otherwise, it's not. If you see anyone that is negative among them, that means it's not positive definite. So the condition for a symmetric matrix to be positive definite is that the eigenvalues of A must be positive. That is, all your lambda must be positive. So look at this one now. Show that a matrix A, which is given as row 1 to be 4, 2, 2, row 2, 2, 4, 2, row 3, 2, 2, 4, is a positive definite. How do you do about this? You find your ladder. You first introduce you find your characteristic equation, which is the determinant of A minus lambda I. You know your I, you know your A. When you do the operations there, you find your lambda. You find your lambda and all the values are positive. Then A is a positive definite. So you go and solve that on your own. Find the values for your lambda. Here, our lambda is 2 and 8, which is a positive value. So the next one, another subsection that we have here, the criterion for determining a positive definiteness of symmetric matrix. The criterion for determination of positive definiteness of a symmetric matrix. Definition now. Principles of matrix. Given a square matrix A. Suppose we are given a square matrix, a n by n matrix A, which is given here. The principles of matrix A are submatrix form from the first high rows and high column. High row and high column. The principles of matrix of A are given as this. You know when you are finding your determinant, you won't find determinant if you pick A. If you pick the first value, that is row 1, column 1, you know you are going to cancel out the row 1 and the column 1. Then you consider what you have you consider the other values, the other entries. So if you can find the other entries and you find that their determinant is positive, that is what this case is telling us. That the submatrix of A are the submatrices formed from the first I row and I column. The principal matrix, that is everything there, must be positive. A symmetric matrix A is positive definite if and only if the determinant of every principal submatrices is positive. The determinant of every principal submatrices is positive. If you pick the first one, pick the first row, first column, you cancel out that row and the column, you have another matrix. If you do the operation there, you have a positive value. Look at the second column, do the necessary thing there, you find the determinant is positive. That is the condition that can make a symmetric matrix to be a positive definite. Let's look at the example we have here. A matrix A is given as 2 minus 1 minus 3 minus 1 2 4 then minus 3 4 9. We want to show that this one is a positive definite. You have 2, which is row 1 column 1. If you bring out that 2, you find a determinant. That is, you cancel out the row 1, cancel out the column 1. You are left with 2 4 4 9. Then look at the second column. You have minus 1. That is minus 1 minus 1. Or cancel out the column 1 and the row and the column 2. The row 1 and the column 2. Row 1 and the column 2. So you are left with minus 1 4 minus 3 9. Then on the column 3 now, you have minus 3 plus minus 3. Then cancel out the row 1 and cancel out column 3 because we are dealing with row 1 column 3. So cancel out row 1 and cancel out column 3. So you are left with minus 1 2 minus 3 4, which is given out here. So those matrices that you have, those submatrices that you have, find their determinants also. If you find the determinants of 2 4 4 9, you will see that it will give you what? It will give us 18 minus 16, which is 2. It's positive. Look at the second one, which is minus 4 and minus 1 4 minus 3 9. Find the determinant of this submatrix. You will have it as minus 9 plus 12. When you find that, you see that we have 3, which is positive. So the submatrix there is positive. Look at the third one on column 3. You have minus 1, 2, minus 3, 4. When you find the determinant of this submatrix, you will have minus 4 plus 6. Minus 4 plus 6 will give you 2, which is positive. So you can see that the submatrix you have here, their determinants are all positive. So that is the condition that can make us to conclude that this particular symmetric matrix is a positive definite. It's positive definite. So assignment for you now. Examine for definiteness of the following matrices. You have to determine the definiteness of these matrices A, B, C, D. Do that and upload the assignment on your LMS. Follow the examples we did here. That is to find the determinant, the submatrix that you have here, find their determinants. If they are both positive, then you conclude. So do that and upload at the appropriate time. So we want to look at bilinear form. Bilinear form. Definition. A functions of n plus n variables. A functions of n plus n variables x1, x2 up to xn, and we have our y1, y2 up to yn of the type b of x, y, which is the summation from I equals 1 to n, then the summation of j from 1 to n of aij, xi, yi is given as the transpose of x multiplied by a, y, where your A is an m by n matrix and aij's are real, they are real values, is called a real bilinear form. Is called a real bilinear form. Example, we have a matrix here which is x1, x2, x3. That is a vector multiplied by a matrix, say A now. Say A, 1, 0, 0, 2, minus 1, minus 2. Then your y, look at the standard form, you have S transpose A y. So that transpose of S is the vectors that we have here. Then your y is the column vector y1, y2. So when you do your multiplication, your matrix multiplication, you multiply the transpose of S with A. The product you get, you multiply by the column vector y, and you have the equation. This is a real bilinear form. The n by n matrix A, which contains all the coefficients of bilinear form, is called the matrix of the form 1. If xi and yj are independent variables, the rank of A is called the rank of the form. That is, whatever the rank of A is, will be the rank of the form of that matrix. If the matrix of the form of that form, the matrix of this form is a symmetric one, the form itself is also called a symmetric matrix.